right, so our next project is going to be a good system for smart cities. We'll have team members, Dr. Dev Niyogi from the Jackson School of Geosciences, who's presenting using AI to forecast weather conditions at the 2024 Paris Olympics, followed by Dr. Yiming Shu of the School of Architecture, is presenting Transportation Digital Twin for the City of Austin. Dev, go ahead.
Well, good morning, everyone. It's a tough act to follow a Robo Cup, I guess, but maybe it should be in the next Olympics. So this is what it is about. I think I had that email from Leah, which guided me to say that we should showcase something which could be based on work we are doing with the Good Systems project, creates a prototype, and then could be used for a societal good. And so that's essentially what we are going to try and show here. I acknowledge a large team, even though it's just my name there. I just happen to be representing a larger one, and you can certainly go to our webpage and get some more details, which is the texaslab.org or the UT City Collab, and we have Charles Puma from the City of Austin here who can provide more details about that collab and how we have developed this as a partnership between the city and UT for developing good system approaches like using AI for digital twins for city operations and so forth. I'm also representing a group that we have started developing in the last year with UNESCO on the development of these digital twins and collabs for use across different cities for developing the kind of things we are doing here. So that'll be something more I can talk about if anyone's interested in more of the international application of what we are doing. Well, so the first thing we are doing is when you say what's a digital twin from a city perspective, that comes up as a definition. Is it simply an overlay of data sets? Is it a decision tool? Is it an application associated with some aspect of interoperability of data, or is it all of it, et cetera, et cetera? How do you know it is a digital twin and not simply a GIS system, for instance? And so we have been having a series of community workshops with about 30, 40 partners across the globe in trying to come up with this definition. We had one really good breakthrough workshop at the beginning of February, which was more with regards to the microscale aspects of buildings and energy system. The next one is in April, where we are going to be doing this with the WMO, the World Meteorological Organization, with regards to what it means at a regional weather system. And then there's a third one planned in line for the cities and the Intergovernmental Panel on Climate Change special issue in trying to say how digital twins fit within the context of cities and decisions and so forth. So a lot of definitions, application case studies got discussed in terms of how we are using digital twins in this context. One of the things that we are doing with digital twins is that models and our understanding of the system has really evolved. Computational aspects have also evolved. What is the Achilles heel here is the input that is required for this data. Many of these models require parameters which are not measured. Many of these models require information which is not really available at every street corner. So how do you generate this data in an open, global, accessible way has been one of the things we have been doing in an effort known as a Digital Earth. This is part of one of the most famous effort of Digital Earth is something known as Project Destiny, which is a Destination Earth project by the European Union, almost I think a 1.5 billion euro project that they have put for the whole operational aspects of how Europe will be doing forecasting with weather forecasting aspects. But a tiny component of that is with regards to what we do with the cities, and we generated the first global building height data sets for all cities across the world. You now have building height data, which is fit for purpose, meaning it's one thing to have the data, and the other thing is to try and link it with the models that are required for creating the environmental parameters. Environmental parameters like building energy load, or it could be the heat stress that's associated with the building and so forth. And we applied it for different cases, say in Chicago, Baltimore, Houston, and other lovely places that we all know of, for thunderstorms to other things that come in. Right here within Austin, what we have used that then for looking at an unprecedented 5 feet or 2 meter per grid spacing, temperature mapping across the city. And what that does is you can look at shade, angle of the sunlight, trees, etc., and then come up with what could be some of the regions which are much more warmer, cooler, open, etc. And this thermal scape is something we have been making available for different applications which have things related to the heat, energy, and other things that could be of use. One early success we had with the digital twin was to work with the Austin Fire Department, and where we have apparently hundreds of potential burns going on. Thankfully, none of them make news, but there is smoke that comes out of it, and there's interest how this smoke might actually be dispersing and contributing to our pollutant loads in the city, and then seeing how this could be changing. Another project that we had with Bentley Systems, now CCM, has been to try and look at the campus as a twin, called the U-twin, and then now we are expanding that to call Aust-twin, which is the Austin as a digital twin. And every government building, public building, what is its energy use? What could be the energy use in the future? Whether it needs retrofitting in terms of making it more carbon neutral or more heat efficient, those sort of data now that we can generate with regards to what's available from the system. One of the interesting things that happened when you have such data and tools, resources with these digital twins is to look at hurricanes that particularly make landfall in cities. That's one of the enduring challenge we have because hurricanes are a large system, but the biggest impact and cascade starts occurring when a hurricane comes towards a city like Houston. And so in that context, we had been doing some studies, and we had a ready-made case study with Hurricane Beryl, which came our way last year, if you recall. And almost all the models were saying early on that this was coming towards Austin. And we had Central Texas really getting into a panic mode at that point. But surprisingly enough, we were running some of the AI tools on that, and each of that model was actually showing the storm going towards Houston 5 to 7 days ahead of what the physics-based models were saying. And so this really became a challenge of, yes, this is happening, but the frustrating part of an AI model, the why part, the explainability was not there. And so we had been working on these aspects of how do you explain these results, even though they are good results, and are they always going to be consistent, et cetera. So this is the case with the Hurricane Beryl, where we are actually running a physics-based model with a MOA we have with NOAA Hurricane Research Division. That's between UT and NOAA Hurricane Lab now, and the AI-based system about how the rainfall and track would be. So this is just showing basically that earlier the physics-based model on the left was showing the model was coming towards Central Texas. If you look at the track, it will show coming towards Central Texas. And on the other hand, GraphCast, which is Google's system, showing it going more towards curving and going towards Houston. And reality is that that is how it essentially became at that point. So what we then have been doing was taking this knowledge of our weather systems, of the thermal data sets, and we participated into something which is known as a research demonstration project of the WMO, the World Meteorological Organization, and part of using AI for weather forecasting during the Olympics. And here it was that we were doing it in a blind test. These were different Canadian center, European center, the German weather forecast. We had UK Met Office. We all are looking at the same data. We are running our models, running it through for, in our case, at night. And then next day morning, our 8 a.m., we are all showing what are our forecasts. And we are comparing what we forecasted yesterday by looking at the observations we got today. So it's a real blind study. No one knows what the weather is going to be. And we were working on all aspects of that. So ours was the only one, so to say, with the AI-based system. Everyone was based on the physics-based system. And so it was a really nice challenge in that setup. So it was based on, again, the GraphCast tools that we had used for the hurricane aspect. We did not have enough training data for Paris. So we had to actually test it over DC. In fact, Adi there and several others worked on that, testing it over DC, then prototyping the buildings from Paris, and then redoing some transference and trying to see this could work or not. So here's an example, and what you're essentially saying is a temperature, time series, and how each of the different models do that. Our model gave a lot of spikes in the jiggity thing, because in the numerical schemes, you sort of do some muting and don't allow for such variability. So this was just a free flow model, but it is basically in the ballpark. The thing about it is the physics-based model for the 24-hour runs take about 2 hours to run. Hours post-training take about, 150 seconds or something. So it's a pretty rapid, fast system that you can do with regards to once you train it and make it available. Temperature forecast, spatial variability in forecast, how it is going to be changing. All these things were really dramatically there with such a poorly trained model with what we have. In closing, then what we did was learned with what we had done with the Austin thermalscape, and then there was a question on the last day when we had the marathon. The organizers had an option to shift the marathon by 1 hour either way to see if this will be better for the athletes to compete, because it was supposed to be a very hot day. And so the question then came was, should we change the timing? Clearly, all of that is classified. They never say what data they use, what they're going to be doing, but it was nice to provide this data. And had this been running, what you will see is that it's actually the bird's eye view of how the athlete would be experiencing the thermal comfort, how the audience will be experiencing thermal comfort through the entire marathon track. And then that was something we did in terms of taking this to the group and so forth. So it worked well, and we then had more conversations when in Paris with UNESCO, and that has led to the creation of, as I mentioned, UNESCO using this as a template that they want to work with, particularly the Global South, in terms of how they want to work with cities for AI and forecast and good system in terms of data being a feature that is not readily available, and I'll be more than happy to talk more about that part. So thank you very much, and I think I'm told I should wrap up. There it is. Thank you.
So weather models have been around for a long time, but you refer to yours as AI. What do you say is a distinguishing difference between legacy weather models and yours?
So the legacy weather models have been around for a long time, meaning about 50 years, and they're all physics-based models. They go from the first principles like continuity equation. They treat air as a fluid. Air is a fluid. So it's a really fluid energy mass balance based off first-order models that you do from the physics of the problem. And you're solving them in a numerical schemes, which are sort of like the leap-forward technique in the prognostication mode. You start with prescribing the initial conditions based on observations, that this is what the atmosphere is right now, and then you're solving those multitude of equations at every time step, 30-second, 90-second, into the forecast. That's our traditional model. The AI-based model that we have is that, let me back up a bit. When I said the initial conditions, meaning what is the state of the atmosphere when we start the forecast, that is based on what we call a global analysis, which is the balloons, the satellite, that are all interpolated to give a gridded initial state of the atmosphere, both at the surface and through the vertical. And that initial state is used to generate the first guess for the model, so to say, in the numerical weather prediction. In the AI mode, what we are doing is we tested the data, that global data, and trained the model for the last 20 years or so, and then just had it available that given the weather condition, what could be the forecast for the next 12 hours. And so the AI-based model basically was a deep learning algorithm that was trained on the past data to be able to predict the next 24 hours. And so the training, of course, took time. It was done on the TAC with the H100s here, but the running was rapid in that part. So the difference here was it was completely data-driven, not physics-based at this point. That was the difference in this part.
But you use the same data.
We use the same input data across the models, yes. Yeah, thank you. Yes?
Thank you for this very interesting presentation. What strikes me is that when you use generative AI, what are the challenges of finding black swan events? And how do you actually control for that?
Brilliant question. I mean, one of the things that always bothered us is two things. I mean, I've looked at this, and I got unfortunately quoted in a different way. I'd said these AI-based models are like a cheap insurance. You never know whether they're going to work for you when you really need it. Yeah, but the reality is, so we started testing these models because they're tested on a known data set. And by reality, an extreme weather event could be completely, as you said, a black swan event, which is not within the sample population we had. And so what we did was we tested some data which did not include any of such event. There was one event in India where we had something like 74 inches of rain in one city, in one part of city, not the other part of city. So that's like a completely non-predictable way of doing forecasting, even for a dynamical model. We had looked at hurricanes, which had rapidly intensified. We had looked at heat waves, which have come in. And without even prescribing that sample period, when we tried to model those events, it is really remarkable that those events gets captured. And here's the difficult part, trying to answer the why. And that's where we are now looking into some of the causal loops to try and understand, even looking at some physics-based guidance on whether we can use those as a boundary condition to work with the more explainable models and so on and so forth. So the good news is they are capturing the black swan events. Not so good news is we don't know why. Yeah.
I have a quick question. For time-based forecasting, have you noticed a difference between the AI predictions and the traditional physics-based modeling in terms of like a day out versus a week out versus maybe even further, and which system is more accurate at which time scale, if there is a difference?
Thank you for the question. Chaos, as you know, as a problem came from weather forecasting because our errors in the initial value starts blowing up such that the noise is more than the signal. And so there is a predictability associated with the weather forecast, which could be, say, after 5 days, 7 days or so, it starts becoming that the noise is as good as the signal. So we don't necessarily apply weather forecast for 7 days, 10 days, or beyond that. These AI-based models seem to have a pretty good knack of going into a period beyond that, into what we call into a medium range forecasting, 14 days, 20 days kind of outlook. It's also getting into the norms of sub-seasonal forecasting, what could be into the next month's forecast and so forth with regards to higher, lower weather and so forth. The thing about these models is that a weather forecast or a dynamical model can give you everything in the atmosphere. It could be the jet stream, the contrails, the clouds, and everything. These AI-based models are targeted for a specific parameter that you might have, something, say, for energy production or for air quality or heat stress and so forth. So that's the difference in terms of it being fit for purpose rather than being a general purpose model that is available and everyone can develop output. To solve that problem, and I see my second speaker come up, and I really invite you to be up, is that we have generated the first AI-based reanalysis. So the last 40 years of data set globally are now available, sitting with us, and that's the first AI-based system. And that is what is being used almost by everyone when we are looking at what we call the reanalysis data sets in a global context. So we're making some progress next year. Okay. Okay. Well, thank you very much.
Thank you, Dr. Niyogi, for bringing this concept of digital twin to us. And today I'm going to talk about our digital twin. And good morning, everyone. My name is Yiming. I am currently a postdoctoral researcher in School of Architecture. Today I'm going to introduce our work on digital twins and LLM agents for smart cities. And before we dive into our project details, I want to introduce our research team working on this project, including our team leader, Dr. Jupen Jiao, and our researchers, Jian Park, Huihai Wang, and Dr. Kijin Song, and me. Today I'm going to introduce 3 components of our project, including a 3D digital twin model for the city of Austin, a web-based transportation digital twin, and an LLM agent for smart cities. Let's start from the 3D digital twin model for the city of Austin. As we can see from the video, we developed a 3D city model of in real world scale, which means this model this is a model with accurate geographic coordinates and measurements. And this 3D city model provides us an environment for simulation and visualization. And it can also enhance realism and spatial understanding. As we can see from the left side videos, we can visualize electricity consumption of the buildings, and we can also visualize the noise from the traffic. To develop this 3D digital twin model, we use NVIDIA Omniverse platform, and we also utilized multiple tools, including CCM, Google Maps, OpenStreetMap, and Blender, and so on. And now we already have a simulation environment, but we want to do some simulation, but we still need some simulation tools that fit in this environment. So we decided to develop our own simulation tools. And today I'm going to introduce this transportation digital twin for transportation simulation. And this tool was developed in web platform, and as we can see, it is based on the real network and maps. And most importantly, it is very easy to use. Unlike other simulation tools, we do not need to install any software. We do not need to set up your environment in your own computer. You can just go to the website and start your simulation with some clicks. And here is the interface of our transportation digital twin. Here is the base map and for the display, and there are some buttons for simulation control, and there are also some visualization tools to visualize simulation data, such as traffic volume, the traffic speed, and the noise, and emission, and everything. And also we have some input boxes for the simulation configuration. And we also have a dashboard for real-time status display, which can show us real-time average speed, real-time delay of the neural network. And also there is a summary of this simulation results. And we demonstrate our transportation digital twin using these three scenarios with different traffic volumes. And the scenario one has a lighter traffic load, and scenario two has medium traffic load, and scenario three has the highest traffic volume. And we can see the differences between these scenarios can be observed by the animation and also by our simulation results. And as we can see, the scenario one has the largest average speed and the lowest delay, and scenario three has the largest delay and lowest average speed. And of course, this web-based transportation digital twin can be connected to our 3D city digital twin to display the simulation in a 3D environment. And here is the intersection near UT campus. And now let's talk about the LLMs. And we developed 2 LLM agents for smart cities, including including an agent for emergency preparedness and response, and another agent for urban informatics. And these agents are powered by GPT-4 and also technique including RAG and fine-tuning. And by doing this, these two agents can generate high-quality responses within their own domain. And also, this agent is available in different languages, including English, Spanish, Korean, Chinese, and so on. And the agent named SafeMate is for emergency preparedness and response. And as we can see from the slides, it can generate a response and provide information, including the text and references to a website, and also we can provide some links to the Google Maps. And for the Open City AI, which is for urban informatics, it can conduct data-driven urban analysis and conduct calculations and predictions for within the urban smart city and urban domain. And for example, it can estimate the housing price for an area, and it can also do predictions for the population increase. And these LLMs agents are based on the data we collected, and also we connect this agent to the internet, to the Google Maps, so that they can provide links to these sources. By doing this, our LLM agent can generate high quality response to the question of users. And thank you, and I'm open to the questions.
Yeah, thanks, Deb. Thanks, Yiming. We actually, okay, one question, but yeah, please.
Thank you so much for your research. I know from previous presentations that your lab has had a good connection and relationship with the city of Austin. So I wondered if you could share a little bit about that collaboration, and if some of the work in the digital twin is informing how the city of Austin approaches some of the mobility challenges in the city.
Okay, thank you. As Dr. Niyogi just mentioned, we have collaboration with Dr. Niyogi's lab and the City of Austin for the fire digital twin. And I think the City of Austin, the fire department, is already using our digital twin for the fire monitoring and for the prediction of the fire spread and smoke spread, and to improve the fire response and improve the public health. Yes, and our imagination is to expand our collaboration with digital twin we are currently working on, like for the transportation usage and for other usage.